Okay, good evening, everyone. I want to welcome you to our talk tonight. We have the history of the modern attack submarine by Captain James Bryant. My name is Stephanie Sandoval, and I'm the Public Archaeology Director at the San Diego Archaeological Center. I want to let you know about our next living room lecture. We have the Archaeology and History of the Torrey Pines State Natural Reserve by Kathleen Dickey. That's on September 17th, and you can sign up through our website. Tonight for questions, please use the question and answer feature, and you can find it on your Zoom control panel. And go ahead and submit questions at any time, but Captain Bryant will take questions at the very end of the presentation. I'm very pleased to have Captain Jim Bryant with us tonight. After a long career in the US Navy, he found archaeology, or archaeology found him. And since he has been one of our most passionate advocates for the Center in Southern California archaeology. And I tell you, he brings more energy to the field than those young college students that are fresh out of school. So I'm very happy to have him with us tonight. And without further ado, I will turn it over to Jim.
Good evening. I'm Jim Bryant, and I'm here to give you a little lesson in submarines during probably the most developmental period of submarines from World War II into the first truly modern submarines. And this background picture here is a great example of that. On the right here, you've got three submarines here moored in Subic Bay in the Philippines. What a wonderful place to visit. Enjoyed my time there. And these submarines are moored in the inner harbor, the Typhoon Harbor of in Subic Bay. And on the right, you have what looks like the USS Darter, a diesel-electric submarine, a fairly modern diesel-electric submarine made in the 1950s, the middle of the 1950s. On this, all the way on here on the left, you see what looks like a counterpart of that, but it's not. It's a Skate Class submarine, a nuclear-powered submarine. The first production models of nuclear submarines after the original Nautilus and Seawolf. And in between, we have what this whole brief is going to culminate with is development. This is a THRESHER Class submarine. Now you would say it's a permit class because THRESHER was lost, but I still call them THRESHERs, and we'll do that throughout this brief. One thing to look at here is look at the superstructure on this diesel submarine and this nuclear submarine. And look what happened after some modernization. We got rid of that superstructure and we moved, these have bow planes up here. We'll talk about that shortly. And moved into fairwater planes up here on the sail of the submarine. So let's talk about, oh, we're not changing channels. So let me stop share again and go back. Here we go. And there we go. Okay, this shows you that I have some background in submarines. You notice down here that I was selected by Admiral Rickover in 1960. It was a smiling Admiral Rickover. He did not give me any of the harassment you hear about these great stories about the Rickover interview. He smiled at me, told me to write a letter to him every month, tell him how many hours I studied, and that I was in the program. That's unusual. I served on older Skate Class submarines, one I just showed you. I've been a chief engineer of a submarine. This one had an engine room just like THRESHER. And I served on three THRESHER Class submarines, Permit, Haddock, and then had command of Guardfish. And then ended up in the Pentagon as a political military officer in which I dealt with naval reactors. Now, part of my research on the THRESHER, I came up with this brief. And a year ago, I filed a lawsuit for the Navy on the records on the loss of the THRESHER. THRESHER was lost over 57 years ago, and there's a lot of information that has not been released. And I cannot give the Navy an excuse to ask the judge in this lawsuit for a protective order. That would be, the Navy wanted so that I would submit everything to the Navy first where they could redact it and then give it to the judge. Right now we have a deal that I give it to the Navy and I give it to the judge, and before it gets put into public record, the Navy gets a chance to look at it and see if it should be redacted because they think it might be classified. And therefore I need a disclaimer. And my lawyer says I need to do this, and I agree. It's very simple. I'm not representing the government. The opinions are mine. And most importantly, the bottom one here is I've derived all my information from open sources. Wikipedia, several great books, because I don't want anyone to say that, well, you're using your knowledge and therefore you're vouching for this. So I don't vouch for the accuracy of these sources. In fact, some are inaccurate, but I chose them because they give you a good picture of learning about submarines and learning about how they were developed. An example here is that the Navy classifies all submarine operations below 800 feet as classified. I used the test depth of THRESHER Class submarines, and I found particularly some books that I could say, and this test depth is everywhere. If you go look in the Wikipedia, whatever, I'm not saying this is the right depth and things they said. I'm just giving you as an example. It's important to test depth because there was a great quest for depth in the production of modern nuclear submarines, and I go through the why that is. So I'm going to teach you how submarines work. I'm going to give you a little qualification course. You will not earn one of these various submarine warfare pins through this, but hopefully you'll learn more about how submarines dive, submerge, operate. First thing, submarines carry torpedoes. Torpedoes are ship killers. In the late 1880s, they developed the torpedo. The torpedo allows a small ship to sink a big ship. It allows a little tiny aircraft to come in and threaten and sink larger ships. But only submarines deliver stealthily the torpedo. The background picture here is a sink exercise, and it's a Mark 48 modern torpedo going off underneath the keel of this destroyer. You'll notice that destroyer's back is broken, his keel is broken. Definitely a fatal blow to that ship. That's why the stealthy delivery of torpedoes by submarines is important. Start with some of the older submarines. Here on the left, we have halibut. Older submarines had two screws. They were in forward of these control surfaces. The rudder is here, upper and lower stock rudder, and you have stern planes. And they had bow planes. Here is a World War II diesel submarine with its bow planes rigged out for operation underwater. And it'd be very hard to operate on the surface or try to moor alongside the pier with these bow planes out. So they rigged in on the surface. Okay, let's start here at the stern, at the aft end of the submarine. In the Navy, we call propeller screw. And in a modern submarine, the screw is aft, is behind the rudder and the stern planes. Stern planes, you have a horizontal stabilizer. In the middle of it, you have what the aviators would call an elevator. This changes the water flowing across it, changes the angle of the submarine up or down, and then the screw drives the submarine up or down. As I showed you earlier, the planes forward used to be in the bow of the submarine, but that created a noise problem. So they were moved for a period of time to the sail of the submarine. That created a problem because they couldn't be rigged in or they could not be retracted. And if you had to go through the ice, for example, your fairwater planes had to be put into an under ice position so they could break through to the ice. Modern submarines have propulsors instead of screws. That's modern submarine, more modern submarines that we're going to talk about today. Up until the middle of the 1950s, they called this part, what we call the sail nowadays, we called it the conning tower. And that's because here's the bridge of the submarine. You step down one hatch, down a short ladder into this conning tower area. And that's where the captain fought the submarine from. That's where all the fire control system was. Your sensors were there. And, but we got beyond that. Sonar, all submarines have sonar. Even in World War I, submarines have sonar. So here's the classic picture of a destroyer sending out a sound wave. It bounces off the submarine and returns. It gives the destroyer a bearing and range, which they can derive a course speed of the submarine to attack it or track it. Now, it does bounce somewhat off the metal, but it's really bouncing off is the people tank, the big air bubble in here where the people are. Sonar is also passive. Here's a submarine listening to the noise of the surface ship, and it can get bearing rate. And from that, with some course changes and some maneuvering, it can determine a course speed range. Here's some World War II sonars. The one on the left is a passive sonar. It was permanently fixed to the top of the submarine. Hydrophones up here, manually trainable. Another one here on the right was both active and passive. This had hydrophones, this has transducers. And it could send out an echo range. And if you read the World War II submarine captain's books, Flucky on Barb, Dick O'Kane on Tang, you'll know that when they shot a torpedo, they used this active sonar to get that last range to a target they were going to attack. It may alert them, but they did that just to check their solution. For the torpedo, they kept this sonar on the torpedoes going out to make sure they did not turn around and come back towards the submarine. Fairly effective. Submarines also use radar. Now the modern submarine on your right has two radars up there. You'll see a commercial radar, Farino. Everybody has those. If you use that, no one knows you're a submarine. And you have the radar you're able to use when you're at very shallow depth. And that's all used just for navigation, contact avoidance, to get bearing and range so you can navigate. Radar was very important to a World War II submarines. This air search radar was particularly important because submarines operated on the surface. What it really is just a pole antenna with this on the top of it. It sent out a signal, and if a big aircraft showed up, let's say a big bomber at 15,000 feet, you might get 15,000 yard range. Shorter attack, a bomber, a smaller aircraft, you might only get 7,000 yards, but it gave you a warning. They also had a surface search radar, more useful. It rotated, it had a parabolic antenna, and from that they could get bearing and range for fire control solutions. They could also submerge this submarine, what they call radar depth, at about here, which they could operate their radar while they're making the approach to attack a target. When you see a submarine, you see this great big black thing in the water. Well, some of that is free flood. Most of the sail area is free flood. It's open to the ocean. All it is fairing. This fares in all the masts that are up here. There's a bridge access trunk up in here. It's watertight. But the rest of it is flood. Also here up in where the sonar is free flood. The mud tank back here, as they call it, is fairing. The shaft goes through here. You have main ballast tanks. Main ballast tanks are open to the ocean. There's a grate at the bottom. When you, they can be filled with water, and it's a very thin tank up here. And the pressure hull is very thick, and pressure hull is very important. You don't want water in the people tank. Here is a pressure hull. You can notice how thick it is. You can make it even stronger by putting this nice T-beam and weld it on the pressure hull. In this case here, this is a German submarine, World War II. The T-beams are welded to the outside of the pressure hull, which is nice if you've got superstructure fairing over it so it doesn't interfere with water flow, create resistance. Or you can be welded to the inside of the submarine, which means you just lose space. Here's a THRESHER Class submarine. You can see the pressure hull, dark line. You see it neck down here. They call this the wasp's waist. Ballast tanks are up here. The gray line indicates it's a thin metal, 3/4 inch. not very thick at all. And the bottlenose of the submarine up here with the main ballast tanks around it. Inside the submarine, you've got variable ballast tanks. Let's talk about forward and after trim tanks. Not only do they add or remove weight from the ship by adding or removing water from them, but they are able to trim the ship so that when you're at very low speeds, you have a zero trim angle, a zero bubble as we call it. The negative tank here, it can be flooded from the sea. It can be blown. The World War II, you always hear blow negative to the mark. They'd, if they wanted to submerge fast, they ran around with a negative tank full, and then when they dove, they blew it. And the auxiliary tanks, right on the center of gravity. There's usually a couple of these. One of them is normally used for storage, but if you ever started shooting torpedoes in a real war, you're going to need to take all your food out of that and get ready to fill it with water, because in order for you to stay submerged at slow speeds, you're going to need to use that. We have a trim pump that pumps the water between these variable ballast tanks into sea, and a drain pump, important to remove water from the bilges. Submarines are also built with called permanent lead ballast. When you build a submarine, you want to have permanent lead ballast, so in case you change machinery in the submarine, the weight, you can add or remove this permanent lead ballast. And this is designed to make sure that your variable ballast tanks will keep the submarine at a neutral buoyancy throughout your mission. Diving and surfacing. Here's a surface submarine on the left. These are main ballast tank vents. They're closed here on the surface. They're hydraulically operated. For a submarine to submerge, it opens these vents. You see the pretty pictures. The Crimson Tide picture of the ballast tanks venting is very spectacular, very, very fun. Main ballast tanks fill with water. You lose reserve buoyancy. The submarine submerges. You close the vents, so if you need to surface again. There's two ways during this time period a submarine surfaced. It used high pressure air to blow the tanks completely dry, or it's enough high pressure air to get the sail area above the water line to use the induction fans to bring air into the ship and blow the rest of the water out so you have a surface submarine. Buoyancy. Buoyancy is important to submariners. It's important at slow speed. If you lose propulsion, you need to slow. You do not want to sink. If you have a problem with propulsion and your weight is more than buoyancy, then you're going to sink. And if you have no way of counteracting that with speed or pumping water out or blowing water out, you're going to sink and your submarine's going to crush. If you have too much positive buoyancy, you're going to go to the surface, and you can't overcome that by adding more water. That could be a good thing, but it puts you up on the surface. You can get run over by a surface ship if you're not careful. If the ocean is rough, you're rolling around. If you're up there because you have to fix a problem, it makes it more difficult. And if you have some kind of potential enemy around, like the Russians or the Chinese, they see you, and that's very bad for the commanding officer to have your submarine seen by the bad guys. What you want is when you go slow, that you maintain a neutrally buoyant. It's very hard to determine that you're neutrally buoyant if you're going fast. You can carry a lot of weight of water or a lot of buoyancy if you're going fast. So what you do to achieve this is by compensating. Here, compensate. You're doing an estimated change. Let's say you're in port for a couple of weeks. The weapons officer loads a couple of torpedoes. They're heavy. They go in the center of the ship. You're probably going to need to remove water from your auxiliary tank. You need to calculate the water you need to remove. Supply officer loans food. He may store it someplace forward. He may need to move water from the forward trim tank too. Also, during a high-speed transit where you can't feel that you're at a neutral buoyancy, you need to make that calculation. You know how much water the submarine is making. You're guessing how much water is filling the bilges. So every hour or so, you move water out of the ship to compensate for that. Now, when you dive the submarine, the diving officer takes control of speed of the ship. And you normally dive at about 6 knots, at least in this time period. You can carry a lot of weight with that. So the diving officer gets to periscope depth or some depth, 150 feet or 120 feet or whatever it is. And he puts the planes on 0, so they're not controlling the depth of the ship. And he moves water in or out of the ship, moves it around, so you got a 0 trim. And if given the time, he likes to go down to 3 knots, called a good 1/3 trim. That could take a while. If the captain is nervous, if the captain needs to get someplace, maybe you'll cut that short, but you're going to try to get the ship trimmed up so that it changes, it compensates for the calculations up here. Okay, this Chief of Naval Operations instruction can be found on the internet. It has a lot of interesting things that we're going to be using in this brief. Test depth. Test depth is what you dive to test the hull. Electrical cabling, sonar cabling, the cabling that goes to your antennas. And that's normally your operating depth, unless you've got a problem with the submarine, which they limit your operating depth because of some material problem. Now, the Germans in World War II, they could not go into deep enough water. They had to operate in the Baltic, and they developed great big hydrostatic test tanks for their submarines. That was talked about when THRESHER was lost, but it was very expensive and very hard to do, and that did not happen. The instruction says you can exceed test depth, and we'll go into that reason here a little bit later. But you need a good reason. You need some guidance from your type commander if you can do that. Now, collapse depth, calculated collapse depth. We use a 1.5 safety factor in making of our submarines, according to this instruction. If you've got a submarine that's good for, let's say, 1,000 feet, just for easy, your collapse depth will be 1,500 feet. So we always test the hull to test depth. But we test all seawater systems to the collapse depth pressure. And let's go see if collapse depth is really a good calculation. We've lost two nuclear submarines. You note here that this is from Norman Friedman or many other books, not me. And these two depths upon which the submarine collapsed is because the submarine sound surveillance system recorded these collapse events, and they were able to measure the bubble pulse. And from that, Bruce Rule was able to calculate these depths, and they're in his books, why the Scorpion was lost and why the THRESHER was lost. And he goes through all the calculations on that and how I measured that. Let's talk submarine propulsion plants during this time period. This background picture is kind of fun. This is a World War I British submarine. It used electric fuel with steam generators in order to operate on the surface fast. And here's this picture is the submarine getting ready to submerge. These funnels are being lowered. The boilers are being turned off, getting ready to submerge. That's kind of fun. Diesel electric. All of our submarines up into the 50s were diesel electric. You've got two great big batteries, lead acid batteries. Here you've got 4 diesel generator sets. These were really well-designed, well-developed units because they were built in conjunction with our railroad industry, because one of these could be used to power a locomotive. And they were transitioning from steam locomotives to diesel electric locomotives. And the power they generate charges the batteries, or it can be used to drive these big electric motors to drive the submarine. So submerge, you have to use the electric. Diesels require air. You have to be on the surface in World War II. Or through a snorkel. We'll talk about snorkels later. And so you'd use the power from the batteries to run these big electric motors. You can also have direct drive diesels. The Soviet Foxtrot submarine, like the one we have down here at the Maritime Museum in San Diego, the center had, the Foxtrot had 3 shafts. The center one was a diesel only, could only be used on the surface, but it gave the submarine extra speed on the surface. Then we have nuclear repulsion. Nuclear repulsion was developed by naval reactors led by Admiral Hyman Rickover, a very brilliant man, the longest serving naval officer. He was known as, to those of us in the know, as the KOG, stood for kindly old gentleman. And that is because he was ferocious, he was not always kindly, and sometimes a gentleman. He was ferocious in DC, he protected his program, he was ruthless, but through his brilliance and through the great engineering principles followed by naval reactors, they were able to develop a very safe nuclear repulsion program. This slide is interesting. It's far from accurate. Right off the internet. I chose it because it gives I can go through a very quick representation of the very basics of a pressurized water reactor. But it's kind of fun. So here we have the reactor core. It produces heat. Now, if the water here was not pressurized, it produced steam. That's a bad thing because you can't pump steam and you can't transfer heat to the steam generators. And also, it's a very good heat, prevents heat transfer, and you don't want to heat the core too much for obvious reasons. So what they do, you put in these electric heaters up here. You've got a pressure cooker. There's a steam bubble up here, pressurizes this primary coolant loop, so you don't get steam. The heat is transferred to a steam generator, flows out into two turbines here shown in the drawing. Electric generator, it's called a ship service turbine generator in the Navy, and to a main turbine for repulsion. Because turbines spin at a very high speed, you want to keep the screw from spinning at very high speeds to otherwise produces a lot of noise. So you have a reduction gear. You have a clutch, so you can disconnect the shaft. In an emergency, you can use this great big motor, DC motor, direct current motor, to propel the submarine up to about 5 knots, as said by the THRESHER Court of Inquiry. It also has, the submarine has a large battery, not nearly as big as a diesel submarine battery, and it has an emergency diesel generator. So if you get into a problem with the propulsion plant for some reason, you can go to periscope depth, you can snorkel, you can float the battery, you can fix your plant. If you can't fix the plant, you can come home on the emergency diesel and the battery. The steam flows into a main condenser, uses seawater to condense the steam into condensate, which is pumped back into the steam generator. So you got a primary loop and a secondary loop. Works fine, great system. And when Rickover decided to start on this program in 1948, no one had ever produced steam from a reactor. We've had critical reactors, but no one ever produced steam. We're going to talk about starting in World War II because that's when submarines really got good. We'd spent a couple of decades developing great diesel engines, good electric generators, the batteries, technology had improved, and we're going to look at also German and Japanese influence on the development of this modern attack submarine. So let's take a look at World War II. Who did the best? Everyone knows the Germans sank a lot of merchant tonnage. Very impressive figure, but look here at how many German submarines were built and how many were lost. They lost well over half of their submarines. We lost the fewest submarines of all these nations operating submarines. So let's see how we do when we take a look, when we're actually looking at figures of really active submarines. And US submarines performed the best. Here is tonnage sunk per active submarines, because not all of those German submarines were operating. They didn't have 1,000 German submarines out there at one time. So we win, and then Germany second, and Great Britain, and then Japan. Major warships sunk per active submarine. these are things, everything from a light cruiser up above. Here we sank a lot more, and actually Great Britain and Japan had about the same amount. So our submarines were performed the best in World War II. And here, everyone likes to talk about aircraft carriers. This is the number of aircraft carriers lost by all nations. It's interesting to note that submarines sank about as many of all nationalities aircraft carriers than aircraft, and relatively few number of actually sunk by naval aircraft, despite watching movies like Midway. World War II, we got 3 classes: Gato, Balo, and Tench. You've got machine guns. You've got a bridge up here. I mentioned before, you can, if you need to submerge to get away, you'd be stealthy. You open the hatch and step right down into your conning tower. You can operate the submarine from there. Now these submarines all look alike. About the same weight, same speed, good surface speed. But look at this, submerged. You have you've got 9 knots, and you've got it for 1 hour. You can do 20 knots on the surface. That makes you a great torpedo boat. The major difference is that you've got classes is the Gato class, which was a thin skin, with a 300-foot boat. Follow on thick skin, Balo class and Tench classes, they could go to 400 feet and 600 feet in an emergency. And that's very important. We're going to discuss that in some detail. So look at the Japanese, Imperial Japanese Navy. They had the most diverse submarines, all the way from manned torpedoes to these huge aircraft carrying submarines. Some of these submarines could carry 3 aircraft. We did not build submarines this big until the early part of the 1960s, when we started building fleet ballistic missile submarines, intercontinental ballistic missiles. The Japanese submarine force had a lot of missed opportunities. This policy was, first, they wanted to go after warships only, although they did do a merchant ship campaign. Unfortunately, the Japanese World War II was run by the Army, and the Army wanted to use submarines to supply Army bases on remote islands and remote locations. But the Japanese did have some great victory. Here's a great propaganda victory. This is a Japanese postcard of this cruiser submarine attacking an oil depot. It's actually in Goleta, just above Santa Barbara. The skipper of the submarine was a reserve commander who had commanded an oil tanker before the war, and he'd actually gotten oil from this. Japanese got about 80% of their oil from us before we did the oil embargo. Didn't do a lot of damage, but it was certainly a great propaganda. And actually, one of these submarines actually flew an airplane off into the forests of Oregon and bombed them, hoping starting great forest fires and reduce our morale. Then we have the German. This is the workhorse, the most successful submarine, all the tonnage that you saw of the German Navy. It's about half the size, half the torpedo tubes. But remember, we talked about earlier, this air bubble in here is what's receiving the reflection of the sonar beam. If it's half the size, that means it's a harder target. It could dive, that's important, and submerge faster. That's important. During World War II, the Japanese and the Allies used convoys to protect their merchant ships from submarines. Ships would all line up and they'd be protected by aircraft, protected by destroyers and corvettes and ships. What they wanted to do is they wanted to do a night attack. And the Japanese radar wasn't particularly good. A lot of the stories you read, our submarines were able to get in here like these German submarines into the middle of the Japanese convoy on the surface and play torpedo boat, wreaking havoc. Here you see these ships shooting up these flares to make light to find the submarine. The German submarines had to go against a little bit more radar, but they could submerge ahead of the of the convoy, sneak in, and then surface in the middle of the convoy and conduct their attacks. But when they got caught, they had to dive deep, and they had to dive deep quickly to prevent depth charges and ramming. Now, depth charges have two effects. Everyone understands the shock wave. And there's also a slower moving bubble pulse, pressure waves. The shock wave is all the long range and most of the short range damage. Bubble pulse is only a short range, but I didn't even understand bubble pulse until I started studying the evolution of how we got to the THRESHER Class submarine. This bubble, it expands and contracts after the explosion. It can shake that submarine if it's close enough, and it can even, that pulsating wave can migrate to the hull and stay there for a couple of cycles, shaking the submarine and damaging equipment. Now these pictures are right out of the unclassified, the declassified damage to submarines during World War II. Here you've got a squib, explodes, creates a big bubble, the bubble contracts, the bubble expands again, but smaller, contracts again, etc. This diagram out of that declassified World War II damage book, here you see the shock wave. It's a much stronger wave by many orders of magnitude. Here's pressure, here's time. The bubble pulse is slower, but that slower movement shakes the submarine and can damage heavy equipment. So in the 30s, up until probably the early fall of 1941, submarines didn't go below 100 feet. They considered it dangerous. They only went to test depth, which was 250 feet, to test hull repairs. In the fall of 1941, Admiral Withers, Rear Admiral Withers, who had probably been well briefed and been watching what was going on in the North Atlantic with German submarines, took over Pacific Fleet scouting forces. He commanded both submarines and maritime patrol aircraft, long-range patrol aircraft. He ordered the submarines. He was really concerned with aircraft attacking submarines. So he ordered them to dive to 100 feet every time they dove and to test depth at least one time every underway. To escape attack. He also ordered practice war patrols off of Wake and Midway. When December 7th, there were 2 submarines off Wake and 2 submarines off Midway. They had no effect on the attack on Wake. They just never got close enough to do that. In Midway was bombarded by a couple of Japanese destroyers after Pearl Harbor on December 7th, and those submarines didn't get involved in that either. And Withers also gave his maritime patrol guys a bunch of these little practice bombs. I'm not sure whether they're just kind of hand grenades, but if they were told, if they saw a submarine under the water, they were to drop these practice depth charges to remind the submarine that they needed to go deeper. Well, people are starting to realize we needed more depth. The first Gato class was commissioned in 1941. This was the engineering duty officers. This is not line officers requesting. This was engineering duty officers. Started looking at the piping system, the thickness, the pressure hull, and they said, this is good enough for another 50 feet. So based upon administrative review, they increased the test depth of the Gato class to 300 feet. The follow-on Balo Intense classes, they were able to increase test depth because they got stronger hulls. Thicker hull plating, a lot of them used a high tensile steel, which is a stronger steel. They were able to increase test depth to 400 feet and 600 feet if you really needed to save the ship. In the 1930s, we made a couple of submarine classes that were too heavy. We had to cut out a lot of the superstructure. We had to cut things out. So the shipyards went on a weight-saving program for submarines. This resulted in more permanent lead ballast. Well, lead is expensive. And what do you need lead for in a wartime? You need it for bullets. Another engineering duty officer solution. He said, why don't we just make the hull plating thicker? I mean, steel is not as hard to get as lead. So you can see here, they were able to increase the weight of the submarine, reduce lead ballast to increase test depth. After World War II, all of our submarine classes were made with high tensile steel, which allowed 700 feet, which is less than 800 feet. So we can talk about that to 700 feet. And in 1961, the HY-80 steel allowed THRESHER class, according to Friedman and Polomar and Wikipedia, says 1,300 feet. So I just shows you the submarines wanted to go deeper. They wanted to make submarines to go deeper. Now look at this. This is why. The depth charges were set at close patterns because you had to get, look at these numbers here. You had to be within 50 feet to really damage or sink a thin hull, or 20 feet. That's a really hard fire control problem. Greater than 100 feet, you didn't have much damage. You got shaken up, but you know, if you had a good submarine, you could survive that. Also, if you get that depth charge below the submarine, you could fill the ballast tanks with the gas created by the explosion of the depth charge. And that could push the submarine to the surface. Also the blast, the water pulse from the bubble pulse would push the submarine towards the surface. If that happened, you get the submarine on the surface and it could be rammed or exposed to gunfire. And we mentioned already, bubble pulse could stick to the hull for several cycles and cause damage. And here's how they did it. Here's a destroyer laying a pattern. These outward depth charges are by this projector. These are hydrodynamically depth charged to sink fast because it solved that kind of fire control problem. And these were racks just jumped over the stern to produce these depth charge explosions. Quest for depth. Okay, submarines we talked about have a low submerged speed. Get 9 knots for 1 hour, then you're on the surface. That is too slow to break contact with a destroyer easily or to get to a convoy submerged and stay with it. But if you used a burst of speed, if you ordered full to dive and go deep quickly, and then you could slow, you could conserve the battery. Here's a scenario for evading a depth charge. Make my point here. Let's say that, and I've seen data from this in the damage book from World War II. Let's say 40 seconds to get to 400 feet. If that sonar, one of those sonars that I showed you earlier, detected it's following the destroyer, detects a splash, the sub can turn 180 degrees away while increasing full speed, accelerate to 9 knots. It's very likely that if you do this right, you're going to be greater than 100 feet from that explosion in 40 seconds. That also that rapid turning creates a big knuckle in the water, which boils out, and you read the World War II guys talking about the destroyer staying behind and depth charging that knuckle. Then you slow down to conserve the battery, waiting for the next round. And this is even more spectacular. Look at this. If you're in a thick-skinned submarine and you need to go to 600 feet to avoid the depth charges, if you can get that deep, in the Southwest Pacific, there's some shallow water, but if you could get that deep, you're basically impervious to getting really damaged by a submarine. Deeper the better. You put more water between the submarine and the attacker, your sonar is less effective. You might go across some thermal layers that will detect that active sound ranging or their ability to hear you. More time to avoid depth charges. Now, the active sonar of a surface ship can only ping down to a certain angle. And as you approach the submarine, the deeper the submarine is, the longer range away you lose that contact on the submarine. So that you no longer can do a few tens of seconds of maneuvering. Also, you have a much smaller bubble pulse, and if you get underneath the explosions, you don't have to worry about the bubble pulse at all. You may get pushed down a bit. Some submarines had that problem by that bubble pulse, but you're in better shape. Now the Germans were having problems with their Type 7C radar, especially on long-range aircraft, as shown in this background picture. High frequency direction finding allowed the destroyers to hear the submarine wolf packs communicating together, send destroyers or aircraft out to attack them. Improve anti-submarine warfare tactics. One destroyer would sit and ping on the submarine and guide the other destroyer in to make the attack, so there was no problem with losing contact as the destroyer approached. And better anti-submarine warfare weapons, head-thrown weapons. So the solution was the Germans started to develop fairly early in the war with this Type 21 submarine. It was the most advanced submarine in 1945. It became the model for submarines for over a decade. They were big, more batteries, streamlined hull. Look, there's no deck guns on this. It was designed to leave its submarine pens, which were under 30 or 40 feet of concrete, and transit out to where it could submerge and then do the rest of the patrol submerged. It had these ferret-in anti-aircraft guns to protect it while it was transiting to and from its patrol area back to its submarine pens. But with this speed, it gave it a lot of advantages. A first true submarine. There's people who are arguing on this, but it could stay submerged on an entire patrol. It's not a submersible torpedo boat, although it still retains some of the basic shape of it. The Germans worked on a safety factor of 2, so it could go down to 1,000 feet. Quieter, it had hydraulic rams and lifts. That meant that it could get under that convoy, and with that speed I just showed you and the endurance, improved endurance, it could reload torpedoes after it shot its first round, and then reload and shoot again, and then have enough time to get out of the convoy and escape. Faults, like German equipment, over-engineered, very complex. You read that about German armor too. They made their tanks very complex. Russians made them very simple. Modular construction. Here's a Type 21 modular construction made at other places, floated down. We do the same. Here's the Uss Hyman Rickover. The bow section of this, the forward section was made in Newport News, is being barged up to New London, where it's going to go on, attached to it, the other part of the submarine in electric boat shipyard up there. Developed the snorkel. Snorkel had been around for a while, but it wasn't needed because submarines could dive fast. It wasn't until the invention of radar, and especially radar on aircraft, it was needed. Here you've got this great, nice float valve in here. It's coated with anti-radar material so that it doesn't show up on radar. You suck air down this forward pipe for the diesel engines. The exhaust comes up this pipe. Here's a picture of the exhaust coming out. That meant that your horsepower was not wasted exhausting the water. And then what you do is you put a radar detector up here on top of the snorkel mast. So if that plane with the radar starts getting too close, the radar signal gets increasing, then you submerge, go deep, and wait for the airplane to go away. It also had a great sonar system, much better, order of magnitude better than what I showed you earlier. This just means passive sound listening device. They call it the balcony because it looks like a balcony here. What you have is fixed hydrophones all the way around. It gave you superior long-range detection. Actually, the Prince Jürgen, the cruiser that escorted Bismarck out, had one of these on it, and it was able to detect the approaching British battleship and battle cruiser well before they came into visual range, which gave them a heads up. The Japanese, well, the Japanese got some help from the Germans. You can see it has that balcony sonar. But look at the innovations the Japanese had on this Type 201 class. You've got rudder, upper and lower rudder. You've got a single screw aft of the control surfaces. They moved their bow planes back. Now this was a kind of a problem because these were not retractable. And if you tried to moor alongside a ship and you weren't careful, you could sink that ship. It's underwater. It was not very safe. We brought two back to Pearl Harbor to evaluate. One had to be towed all the way. The other had to be towed from Guam. One of the problems was, in order to get this great underwater speed, look at that underwater speed, that's better than the Germans. It had to have batteries everywhere, and these batteries were not very well secured. And if you're on the surface, these batteries could fall over. And the B-29s were wreaking havoc with Japanese industry. And so these boats were not really completed. There were whole sections missing. They were kind of dangerous to operate. And when we got them back to Pearl, we did some evaluation, but it considered that it just, they were too dangerous to operate. Now, when we captured the German submarine yards, here's a picture of some Tommies with some Type 21s here under construction. The big players, the Soviet Union, United Kingdom, and us got some of these to evaluate. We couldn't copy them exactly because they were just too complex, but a lot of the features were used in follow-on submarines. Here's the Soviet Whiskey, a smaller version. Here's the balcony passive sonar up here. And the Zulu, which was about the same size as a Type 21. And our version is a Tang class. And we had we called it the BQR2. This passive sonar was basically a German sonar with some improvements. Poor endurance because it had the snorkel. And when you snorkel, you're not truly stealthy, but it was a great submarine. Now we had all these leftover submarines, these deep diving Bellow and Tench class submarines. We developed this program called Guppy, Greater Underwater Propulsion. And you can see all the things that we added to it to make it, and it became a very reasonable, like German Type 22 submarines, and they lasted up into the early 70s. Then we have the first nuclear submarine, the brilliance of Admiral Rickover and naval reactors. Now we have unlimited endurance, and 23 knots comes out of Wikipedia. I don't know what the real speed is, but it just shows you that it went a lot faster. And the thing is, great endurance. The Nautilus could run in and attack the carrier battle group and run out, and it had a very, very hard time for the destroyers to even gain contact. The sonar window was a very small window in the passive search, and it was very hard to keep up with them. A diesel submarine could hear Nautilus coming. It was noisy, but it was very hard for them to get into a position to attack it because it was going so fast. Then we have the first production models. Built 4 of these. 18 knot submerged, again out of Wikipedia, I think. Basically, you're a little bit improvement over the Tang, more improved reactors. But I mentioned earlier, you have all this excessive superstructure up here, which cuts down your speed. So what we needed to do some research. We needed to find out how we're going to use this great new propulsion system of nuclear power. So we made the albacore, and the albacore was really neat. No torpedo tubes, but it tested all the things that we thought. And here's a lot of the things that were tested. Here's albacore sitting up in Albacore Park in Kittery, Maine. You notice this X control surfaces. This takes the place of both the rudder and the stern planes. It worked very well. It required some computer. That scared a lot of people. Our new Columbia class, the drawings that I've seen in the paper show this on them. Here it is with two counter-rotating screws, but all these things were tested, and it's also used as a high-speed target. But that did all this research on this submarine produced the Skipjack Class, 1959. Here's 1959, and we're still dealing with the improved version of the sonar. 5 compartments. They moved the bow planes up to the fairwater planes for less noise. Same test depth, 5 compartments. They were fast. I use 29 knots. Some things say, some books, Wikipedia says 31. Bruce Rule, who is a SOSUS expert, says that there were 29 knots. They didn't go over 30, but they were noisy. They had a poor sonar platform. They didn't have a great sonar anyway. Here's Thresher here. here's Scorpion. Scorpion sank in 68, and that's another whole story. Here, this great big sail, all kinds of electronic mass in it. So you could sit off somewhere where the Russians were, and you could record all of their radars and listen to communications and all kinds of great things. And we needed to make a sub. The Soviets were building lots of submarines. We needed something that was an anti-submarine warfare. Our first attempt was Tullabee. Tullabee had turboelectric drive, as it says in Wikipedia. It had electric generators that ran big motors. It was a great sonar platform. The torpedo room was moved from the bow, big sonar put up there to the middle of the ship, but top speed was slow, and it was small, and it was hard to get enough food in there. It was just, it didn't work out, but it was a great sonar platform, people have told me. Then we produced the world's most advanced submarine in 1961, the THRESHER Class. The THRESHER. Here we have a great sonar, spherical sonar in the bow. The bow compartment is a berthing area in equipment spaces. Torpedo room is in the center of the ship with the torpedo tubes coming out to the side. Basically call it a modified Skipjack Class submarine with the same 5 compartments. And here you see the torpedo tube shutter doors coming out the side of the ship. You have 2 on port side, 2 on the starboard side. A bigger submarine. It had a lot of sound quieting. It was bigger around, it was heavier. And they reduced the size of the sail. According to the Friedman and Polomar, we got rid of a lot of the electronics mass, but it was designed to go after threatened Soviet submarines. THRESHER was the first really major threat. But Tullabee was a threat, but THRESHER could go fast. This speed is out of, it's not important. It's out of one of several books. I mean, and submarine speed also depends on how fouling and whether it's got a 5-bladed screw or a more bladed screw. But it was an excellent sonar platform. According to Friedman, the test depth was nearly doubled. A very effective sound quality. The machinery, the turbines, the things that were in the reduction gears were built on a big raft, and that raft was sound isolated from the pressure hull. Pumps and motors were sound isolated to their mounts, and there was sound quieting fittings as the fluid came out of that pump, so they would not be transmitted to the sea. Large active and passive sonars. It had a conformal passive sonar array, which is low frequency. Low frequency is long range, and a subrock ballistic missile. It had a nuclear depth charge on it. It used the first computer fire control system, and it went to a steam air conditioning plant, which is a lot quieter than the R12 refrigerant R12 plants, which were piston driven and were very noisy. Here's some of the things. It also shows here, you have these, this whole deck platform is mounted on sound mounts so that any noise created on this deck is not transmitted to the water. The whole bow compartment here, berthing area, machinery, and equipment spaces are sheathed in this aluminum with fiberglass in the center of it, this casing, and that kept from noise interfering with these sonars. These are some commercial sound isolators to give the impression pumps would sit on these kind of things. That big raft I told you about was this a flex coupling would be when fluid came out of a pump, seawater. It was sound isolated in 3 directions so that vibration would not go into the ocean. On the left, you see this is actually a picture of THRESHER. Each of these holes would be a transducer, and it was set up so that you could look down, so you get bottom bounce ranges, You can look up and get surface bomb ranges. And here you have a picture of a conformal array, which would detect low frequency sounds. Subrock, shot from a torpedo tube. The literature says it's tritium boosted. So your World War II nuclear weapons with about 20,000 kilotons of TNT. If you tritium boost that, what do you get? I'm guessing maybe 100,000 more. You know, I don't know. People speculate a lot, but it was a large nuclear weapon, long range. It used that big active sonar up there at long range to try to get a ping, bounce off that target to get the range and confirm that the range. And we mentioned how close a depth charge had to be to a pressure hull in order to breach it. So this could probably breach it at many thousands of yards. I don't know. I don't have data on that, but it was a major concern. Again, your deeper test depth advantages. Just like World War II, you put more water between you and the surface ship going after you. Also, sound tends to bend down in the ocean. So the deeper you are, you get some better, longer range detection. Nuclear depth charges and nuclear torpedo warheads were developed, but again, if you go deep and fast, you have a better chance of escape. Acoustic homing torpedoes were being developed. They were being rapidly developed, and if it's shot from a surface ship or an airplane, it would take much longer down to reach the depth upon which the submarine was at. If the motor operating the torpedo was powered by a fuel, it'd have to exhaust to the ocean pressure, which would reduce its range. So going deep was definitely good for that. It also gave you more vertical room to maneuver for tactics and depth control. If you had a control surface problem, you're less likely to broach to the surface or go below your test depth. And you had plenty of room to maneuver at your high speeds. Well, the world's most advanced submarine sank. THRESHER was lost during a planned routine test depth dive after a 9-month overhaul. This was totally unexpected. This was unheard of. This was a shock. It's kind of like the sinking of the Titanic or the loss of the Space Shuttle Challenger. In fact, people have pointed out to me the Space Shuttle Challenger and the loss of THRESHER have a lot of similar things. I have a follow-on lecture on that if you are interested. Now, people always ask me when I give this brief about Hunt for Red October. So I just slipped a slide in here. Our famous Sean Connery, I think he just turned 90. It's a very fun movie. The ranges are much too close. You're within baseball throw range of, as shown in the movie. Clancy didn't really understand sonar. He kind of thought but operated more like radar. He has in his books he has very quiet sonar contacts with a noisy contact in between. You can still hear the quiet contact. And he has pictures. You got about 3 guys. They're running a submarine. They're maneuvering it around flank speed. You need a crew in the engineering spaces at least to get a submarine to change various speeds. Subject to your questions, comments, and if you want to be interested in join the Naval Submarine League.
All right, thank you very much, Jim, for tonight's talk. We will now be taking questions. Just as a reminder, please submit your questions using the Q&A feature that should be at the bottom of your screen. So we have a question from Cindy. It's actually a 2-parter. Is the major role of submarines today to carry nukes or to observe or other? In the future, how will the role of submarines change? Also, can a modern Navy exist without submarines?
A really modern Navy can't. You'll see most of them do. As for what submarines are doing these days, I'm not going to talk about current submarine operations, but I'm sure that my guess would be is they're concentrated against other submarines. Well, they perform all kinds of tactics now. We have the fleet ballistic, we still have missile submarines that are targeted against our enemies that shoot with nuclear warheads. But as to what nuclear weapons are on submarines nowadays, besides the obvious fact that the Tridents are carrying nuclear weapons, I do not know. I can't comment on that. Did I miss one of those questions?
I think you got it all. We have a question from Jim, which is, which country has the largest group of submarines now?
Gee, that's a good question. I'm not really sure. I would guess us. That's my fault. That's easily available. That's well on the internet. Although I think the Chinese, well, it really depends on whether you have nuclear or diesel. The nuclear submarine is truly superior. People talk about going to us building diesel submarines, but they still cost a lot of money. They take a lot of talent, and they're just not as effective. You know, diesel submarine is really good if you've got islands. Somebody has to approach you through islands or guarding straits, and we really don't have that problem defending the United States. That's just off-the-hand comments.
All right, we have a three-part question from Nicholas, so I'll just give you one part at a time, Jim. The first part is, how has the refinement of the power plant aided in achieving deeper tactical depth and a submarine's ability to evade detection? This is skipping ahead 60 years.
Well, how does the power plant in depth? Well, the records show that Rickover wasn't really excited about going deep. And I mean, and naval reactors in the propulsion plant was really designed to have a powerful thing to drive the submarine around with great endurance. I can't speak upon what they're doing today. If you use the World War II model, I'm sure there's some tactical advantages going deep still today, but I do not know that.
All right, the next part is, how has the Navy integrated artificial intelligence into its ship driving, sonar, fire control, and propulsion systems to gain efficiencies and increase ships' capabilities and safety?
I have no clue. Remember, I'm dealing with a period. My whole studies are, leans upon THRESHER, and this whole brief is based upon what caused us to develop the THRESHER Class submarine. So, and I have no idea how artificial intelligence is really used in submarines.
All right, we have a question from Brian. Why did the Scorpion sink?
Why did the Scorpion sink? That's an easy one. You read Bruce Rule's book, Why the Scorpion Was Lost. There's a great analysis of that from an unclassified tape he got from a university. It was very likely it was a battery explosion. The battery explosion happened about 22 minutes before it imploded, and the conjecture of Bruce Rule says in his book is that the powerful explosion was basically equivalent to 2 20-ton charges of TNT inside the ship. It incapacitated the crew, and the ship sank slowly down to its crush depth and past its crush depth and collapsed. And what caused that battery explosion? Boy, that's at least an hour worth of discussion of conjecture. I studied that in great detail. Some say it's a leaky trash disposal unit. Some say it was a book written by an admiral. Talks about hydrogen buildup caused by changing the ventilation lineup during a battery charge. But and I can tell you that in my discussion with some senior retired admirals, they go along with the battery explosion.
All right, we have a question. What is it like to live on a submarine?
Well, it's kind of like going, you don't have basements here, but it's kind of like living in your basement. And you're very busy because there's lots of machinery in your basements and lots of electronics that always need to be fixed. And then you've got to go out and do your mission, which is to go find the enemy. Books say that we go observe the Russians, we go observe them. One of the Seawolf submarines just came into a fjord way up in northern Norway. One wonders what they were doing up there. But
all right, we have a question from Charles. Could you comment on air-independent propulsion and its position in today's development of advanced submarines?
I know it exists. I know some of the how it works, but you're still pretty limited to speeds. I mean, you don't have to snorkel all the time. You've got to come back, depending on what kind of plant, you have to come back and load things for your power cells. But I assume it adds some advantage, but I don't. Again, I've been out of the submarine business for a long time, and I've been the books I'm looking at are stuff that's in the open literature, and in the time period that I'm really studying, I'm not looking at air-independent propulsion. I do know that we bring diesel submarines up here from South America to diesel electric submarines, mostly made in Germany, to practice anti-submarine warfare against these type of things.
All right, we have another question from Jim. Do you need to go through special mental assessments to serve on a submarine?
No, not really. Nuclear power kind of does that for you. Nuclear power training is very rigorous. It's a year long. You do 6 months in classroom, in 6 months, at least I went through, in operating a nuclear reactor prototype. I did that. Now they've got moored training ships in Charleston. In my experience, I never had problems with adapting of nuclear trained guys. If they could cut the nuclear power program, which is a really tough, good program, you could do it. Now the ones that I had problems with were cooks who got very, they went through submarine school, but they're not put under a pressure course. The guys who ran the electronics forward, for example, and the sonarmen, they went through a lot of training and a lot of testing and a lot of scrutiny before they got to submarine school. So when they arrived aboard, they were pretty well seasoned. But I've had problems with cooks who got nervous in the service and had to be sent to surface ships. But I also have to mention that cooks were probably the most important people on my submarine, because if you wake up to a meal that's really bad, your day is just really terrible. It really sucks. So the crews, the cooks could make or break a whole day on the submarine. So I spent some time, besides in the reactor plant, I spent some time in the galley, making sure that good meals were produced.
All right, I think we have one more question. Just a reminder, if anybody has any last questions, please put them in the Q&A. Otherwise, our last question is, I think it takes a special kind of sailor to choose the silent force. What makes a good submariner?
What makes a good submariner? Well, you have to be technically minded. You have to be able to work very hard and under very long hours. You have to strive to meet very stringent standards. People who like technical backgrounds, who like technology, computers, neat mechanical systems, lot of very interesting mechanical systems involved with the reactor. A lot of neat mechanical systems involving the torpedoes, torpedo tubes, torpedo systems. And you have to want to challenge. Somebody has to want to challenge. And you work together as a team, and it's got to be a team player. Does that help?
I think that's a good answer. And I think that's going to be our stopping point. Thank you once again, Jim, for your talk. And thank you to everyone for attending tonight's living room lecture. Just as a reminder, our lecture series continues in September with the Archaeology and History of Torrey Pines State Natural Reserve with Kathleen Dickey, and that will be on September 17th. For more information on this and our other upcoming events, please visit our website, sandiegoarchaeology.org. Thank you and good night.